Yeah, the topic that I'm going to talk about is streaming first approach to Iceberg with RisingWave. My name is Rayees Pasha. I lead the product team at RisingWave Labs. For those who are not familiar with RisingWave, we're an early stage company uh, pioneering stream processing through a Postgres compatible database. So the agenda for the talk is fairly high level. I'm going to give a quick introduction about RisingWave, and then we'll talk about what we call streaming data lakehouse and our journey into lakehouse, because primarily we are a stream processing database, but how did Iceberg came into the picture and what have we built in the last 1 year. Quick background on RisingWave. As I said, RisingWave is a distributed SQL database, purpose built for stream processing. So sort of a hybrid category here we're talking about. It's a streaming database where we, under the hood, it's like a incremental process model, like similar to what a Flink does, but the interface is similar to a traditional relational database. So think of it like a combination of Flink plus Postgres in one solution. We are an open source product, the core engine, RisingWave. It's open source under Apache 2 license a couple of 3 years back. The company itself, called RisingWave Labs, was founded by Andrew, who was not here, but he worked in this building. So he was the ex AWS person. So there's a connection to this building where we are having this presentation. As a community product, as the open source product, we are heavily invested in community, and we can see the growth in the community. I've shared some of the stats here in terms of our community growth month over month has been tremendous. We have about 8,000 GitHub stars, more than 200 contributors, and a vibrant Slack community. But the true measure is the deployments. Actually, we have hundreds of thousands of downloads, but we see consistently like 4,000 or 5,000 active deployments. Some of them prod. So we see a lot of persistence uses over time. But that's just this open source. We also have a bunch of customers, all those I listed here on the slide. So digging a little bit deeper into what RisingWave is, right? The core product is a streaming database, but our vision is to address more unified data processing from the perspective of streaming, so that the approach we take, it's not binary where it's streaming versus batch, but streaming first approach to address as many use cases as possible. But at the heart of it, that is the stream processing engine. So not only do you ingest data, you process, but you can store the data in the same engine that enables you to have a single copy of data that can address multiple use cases. So from an architecture perspective, if you see the diagram, RisingWave is sort of the vital cog in your data engineering pipeline. So you have upstream sources, which we call sources in stream processing parlance. That could be event streams like Kafka, could be CDC sources like databases that produce updates, could be data lakes, data warehouses. So for RisingWave, all of the sources are, from a data model perspective, think of them like a base name. Because our data model is completely relational. So you look at that as a table, and then you can do all the operations that you typically do with the database: joining, transforming, aggregating, whatever you do with the standard SQL, you could do that with RisingWave on moving data. Basically, you basically it's like assume that you're working with a database, but under the hood, you have this streaming data that's continuously flowing, and you can write all sorts of transformations for ETL or even streaming analytics. And on the other side, once you have transformed the data, because RisingWave features a built-in storage engine, actually custom built for high-velocity data, the data becomes available immediately after transformations. And that's why we can guarantee latency. Here, when we say latency, we're talking about data latency, like from the time it enters RisingWave to the time it's ready for serving. That latency we can guarantee under sub-second, like 50, 100 milliseconds, even for complex pipelines. So from the perspective of the whole, putting it all together, one, you have a compute engine that's able to guarantee ultra low latency, but also the fact that we have a storage engine allows you to query the data right away. And that's where the Rising Iceberg comes into the picture. Now, by default, For ultra-low latency use cases, you use the storage engine that's custom for RisingWave. It has its own encoding for high velocity data and when there is a lot of changes in the data. But what you have use cases that are more OLAP oriented, where you want to do analytics over a large period of time, more ad hoc patterns. That's when the need arose from our perspective to support not only the built-in storage we have, but also something that's an open format. And then we started with Delta Lake, and then started with Iceberg. For last over 1 year, we saw a lot of momentum towards Iceberg, and that's when we started our journey to start supporting Iceberg, and that's what you see in the bottom right corner. Now, from a use case perspective, when I say unified, the data serving capabilities of RisingWave are it's a database, right? So you could basically query the data whether it's stored as RisingWave tables or Iceberg tables. That feature functionality is available completely, but with Iceberg, you also have a choice of picking whatever tool you want to query the data. So I will start with the first initial journey over how we started with Iceberg, right? So our core users are stream processing use cases where basically folks are using us for streaming ETL or streaming analytics, where the assumption is you have a lot of data continuously coming in, you're performing transformations, and you push the data to a downstream system for delivery, or you directly query from RisingWave. Now that's the top part of it, where you basically have a bunch of dashboards, reports, whatever, what have you. But then with the adoption of Iceberg, and a lot of our customers were asking, like, how can I basically do data management if some of my data is in Iceberg? And that's where we started supporting Iceberg as a source, like basically a batch source where you could bring the data from Iceberg into RisingWave, and then vice versa, push the data back to Iceberg if you from all the streaming sources that was coming in. And that worked well for a few use cases. But the problem was always that you have two systems that have impedance mismatch in terms of how they operate. While RisingWave is a build streaming system for incremental processing, Iceberg is more suited to the batch workflow, where latencies expectations are different. So that's when we kind of started thinking about building a full managed service. But before that, let me first talk a little bit about what our initial functionality was. So as I said, RisingWave is a focused wire compatible system, pure SQL system. That's our API, right? So we adopted the same model when it comes to supporting Iceberg as source. So here's some simple command. So if you have Iceberg source, all you have to do is run this simple DDL statement, which basically in which you specify the some of the particulars, like what is the connector, what is the endpoint where the Iceberg data is stored. Like for example, here in this case it's S3, and you also specify the catalog information. What under the hood happens is it RisingWave maps the Iceberg metadata to a RisingWave table implicitly. We call it source. And then once you do that, you can basically treat that external table, which is in Iceberg, as almost like a table that's inside RisingWave. You can do insert select, you can do any of the SQL operations that you do ordinarily, right? That's on the source side. Now, on the sync side, we have a similar another command called sync, which creates sync, where if you say you have a lot of processing that you do on the streaming sources, and you want to write that back to Iceberg, you simply say create and then include whatever the logic you have, and that automatically pushes the data back to Iceberg, right? So with this initial functionality that we provided, all we did was we said you could read Iceberg and you could write to Iceberg. But the ownership of those Iceberg tables was outside the purview of RisingWave. Now that created some of the challenges, right? Some of the customers said, "Hey, our data has a different cadence at which it gets changed. It's very fast changing data because we're talking about streaming data. It's continuously changing. So it does, and it doesn't work well because the RisingWave is processing data at a pace that the compaction and all of the things that required for the Iceberg table was not. Second thing is that inconsistencies, right? You have with streaming system, there is a notion of exactly once, at least once, different types of consistency guarantees you provide. The same data when it's written to Iceberg to all duplicate data or to avoid inconsistencies, those we could not guarantee because those iceberg tables were not under the purview of RisingWave, right? And then the last thing is cost also, right? From business side, you're basically trying to manage two different systems. From OpEx perspective, you have to manage the ingestion path, but also from the storage side, you have to manage separate the different stack altogether another system, right? So all these challenges we had to inherit basically because whatever we provided from functionality perspective for source and sync, that may have solved the immediate problem, but it created new problems. And our solution was to basically say, hey, why don't we go a little further? Because with RisingWave as a full-fledged streaming database has all of the pieces that are required to support our data lakehouse. And then, so we try to repurpose all of that in this concept called streaming data lakehouse. What streaming data lakehouse is the concept means is you don't treat streaming data that comes in as a special case, but as the default case. So if all your sources are streaming, you might as well ingest the data in real time, process it incrementally as opposed to doing ETL in a batch manner, and then organize the data sets in a with a clean data hygiene where you can say, I have bronze layer, I have silver layer, and gold layer, so that you address all sorts of use cases as the data goes through transformations in your data pipeline. So now, obviously, to fulfill this concept, this vision, you cannot keep the data in RisingWave itself because the analytical use, as you can imagine, can span any type of workload, and all those workloads are not supported by RisingWave. So it had to be in an open format, and that's when Iceberg kind of became obviously the obvious choice for us, and that kind of led to manage service. Like we had to build all the capabilities, and the rest of the presentation I'll talk about the features and some design choices we made. But before that, let me pause here for a second to see if there are any questions on at least the overview of RisingWave and the initial features we did. Yeah.
One question. So, if you had to support multi-regions, or if there are multiple copies of the data, how do you guarantee it is to be in a consistent state?
Yeah, so the question is if you have multiple copies in multiple regions. So in this case with RisingWave tables, we have a single catalog, the Postgres back catalog that keeps track of all the copies, even if they're spread across multiple regions. Right? But if it is with Iceberg table that you're talking about, then it's done the Iceberg catalog to ensure consistency across if it's spread across multiple regions. We do not, when we talk about Iceberg managed service, we are talking only about the ingestion and writing of the files. The actual maintenance of those tables is done by the Iceberg catalog and the Iceberg service that you are going to use. Any other questions? So what does the managed service entail, right? So I want to start with a simple command that we run and then kind of peel the onion in terms of what were required to build this. So for us, again, supporting Iceberg, we didn't want to change the interface. We wanted to keep it the same way. The current model that we use with RisingWave tables is a SQL-based system, right? So we use ANSI standard SQL. So we kind of borrowed two concepts. One, the concept of connection, and then obviously the create DDL statement as table is right of you. The connection was the connection statement was used to encapsulate all of the parameters that are required from Iceberg connection perspective, where you would specify what is the type of catalog, what is the location of the data warehouse or the object stored where you're going to store, what is the region where it's stored, what are the security, key and access key secret that you want to store. By doing this, we are separating out the Iceberg environment variables from that of each statement, right? Once you set up this connection, whatever tables or objects you create, those will be the ones that will be applied to. And for this, we basically introduced a new class called engine equals Iceberg. So this is to differentiate between, by default, creating RisingWave tables versus creating native Iceberg tables. So once the connection is set up, you run any command, they will inherit those connection settings for each of the objects that are created. And again, one more thing we added was we allowed users to have multiple direct connections. So you say if you have Iceberg warehouses in multiple locations or multiple different catalog you're using, you could toggle from one to another. So in a way, we basically gave users a choice of what sort of Iceberg implementation they're going to use, and RisingWave just serves as a client to write objects into that system. So to run that simple command, obviously there's a bunch of features we had to implement. One is obviously support streaming ingestion. You saw that at the very beginning when we did the source support, it was a batch source, right? It was more of batch ingestion where if you were continuous updates, they would be batched at regular intervals. Second is incremental materialized use, which is the core feature for RisingWave because this kind of powers a lot of the streaming jobs. We added support for that. Third is table sharing. This allows other systems to read from the tables that are created by RisingWave. Exactly one semantics. This is important to ensure that whatever the data that flows through RisingWave and return into Iceberg is semantically consistent and there's no duplication or data loss. Fourth is the catalog support. Obviously, catalog is the metadata layer. How do you ensure that the initial metadata catalog information that's in our Postgres metastore is consistently stored in different variety of catalogs that are supported there? And then last but not least, the compaction, because with streaming workloads, there's a lot of churn in the data, a lot of small files that are created, and how to handle those small files in a reasonable manner. We had to write our own compactor. So I'll start with the streaming ingestion again. For us, the support streaming ingestion, we didn't introduce any new syntax or any new API. It was simple again, create table stripper. In this case, we are basically reading from a topic, and you're basically specifying engine equals Iceberg. So all of the updates that are coming from upstream Kafka source are automatically stored in this Iceberg table in a streaming fashion. In this way, you could basically what this enables us to do is provide ultra low latency even for Iceberg tables. Materialized use. This is the key feature that I mentioned, right? So in RisingWave, when you have stream processing jobs, these are continuous jobs. So once you create MV statement underneath that, it creates a streaming job that performs transformations as new data, right? So it's like a different paradigm. Think of it as it's not like there is a system that runs jobs at different intervals, but the arrival of the data itself will trigger a computation, and that interface is obviously available in RisingWave. So we added support for that for even Iceberg tables. So not only can you have Iceberg tables, but you can have Iceberg materialized unit. So that as the data is flowing through, coming from the upstream sources, those materialized views will be automatically maintained in Iceberg. And how we do that is we basically use the snapshots. We track the snapshots, and whenever there's a new snapshot, we look at what are the new added files that are there in the Parquet files, and then process them parallelly. So this happens in a continuous fashion. So at any time, when you query the materialized view, you get the fresh data like guarantees of up to in a few seconds. The freshness actually depends on the commit frequency. By default, we set that's configurable, and we set it to 1 minute because of some limitations on how the compactor does. But you could lower it further, so you can ensure that the guarantees can be even a few seconds. And then the table sharing, which is again a key feature. We've listed a few logos here like Trino, StarRock. Other systems can also use, but the basic concept is how do you ensure that if user has a particular system they want to use to query the data, what sort of access requirements you can support. Obviously, you need to be able to access the catalog as well as the object store, both for metadata and not data. In our case, for implementation, we basically, again, leveraged our implementation and our Postgres SQL design. And we basically, for access, users have to use connection strings, which are already supported for RisingWave tables. The same will be available for Iceberg. And then we introduced two new metadata tables called Iceberg tables and table namespace. These capture all of the information about Iceberg in catalog in our meta store, which users can query. And then the access controls, we use the existing built-in permissions. Like we have RBAC control for RisingWave tables. The same RBAC control model was applied on new Iceberg tables. And then the object store access, we use temporary credentials with IAM, specific read-only IAM roles to restrict access. So this is sort of the model we adopted to allow access from other systems. And then the next feature was the exactly one semantics, as I mentioned. That's one of the challenges because of the fact that you have this data coming from stream sources going through multiple layers. Now, to guarantee the reliable writes, we need to make sure that there's no data loss and duplication, right? Especially when there's an error, and if you have the writes that are in flight, how do you ensure those are committed or rolled back, right? To do that, we implemented two-phase commit protocol, basically, that basically persists all the data. First, data is written to a durable log, and then the metadata is captured when you store the each writes log location. And then once the commit is complete, that's when you basically clear that particular log location. And if there is ever a crash, for example, on the recovery logic, we go back to that last committed point in the metadata and then either recommit the changes of the writes in flight or we roll back everything. So in a way, we guarantee atomicity using this approach for the semantics, exactly one semantics. And then on the catalog side, although we support all of the different types of catalog, our journey kind of started with more SQL JDBC catalog, right? So because we're a SQL system, we have a built-in meta store for our product. We leveraged that to start with in the first version. And then we started supporting Glue for AWS users. And now, obviously, we support REST catalog with Polaris support. So, but now the default version is the REST catalog, but users have a choice. They can pick based on where they're hosting Iceberg to be so that they can avoid vendor lock-in. Last one, in terms of the capabilities, is compaction, right? As I mentioned, streaming data has a lot of churn. It's very spiky. It can go up or down. So compaction basically is critical. How do you merge those small files to reduce the pressure on the metadata and also improve query performance, also the cost of the optimization? Now, the traditional approach has been like compaction using Spark jobs and other things. And those are great if the data has certain patterns that fit that particular batch model. But if your data is very streaming, it's coming at a much higher velocity, it becomes a challenge, because you have a lot of complex tuning you have to do at the Spark, and it assumes the user has advanced knowledge of how to tune them, right? So we rewrote. This is the big feature, honestly. It took us a lot of time to build it. We wrote using Rust. The RisingWave as a system is also written in Rust. So we combine Rust with data fusion, and a lot of the things we've seen in terms of the cost as well as the performance have been amazing. In terms of the GC overhead, for example, a lot of the issues that you run into with traditional compaction with JVM-based compaction, we were able to work on. A few things I wanted to talk about the design decisions. Like I know the features were there, but we had to make some design decision calls. Like for example, how do you handle large scale updates? As I mentioned with the streaming update. In Iceberg, there's two ways. One is you can do merge and read or copy and write. Obviously, we are more write heavy, so we use merge and read. Our support, one of the things because of the fact that there's memory limits, we had to use disk spill as a way, an extension of our cache to allow for large scale changes to be merged. And in terms of our implementation, we support both equality and position deletes. And then we use basically a SQL, our own query engine, to process the delete files. And the way we do that is whenever there are files to be ingested, we add metadata from those files. Like for example, sequence number, what is the file path, and what is the position in the file that got changed. And then we resolve those based on the before and after files. We basically do a left-hand join to see what changes are on the new versus old, and then clean up metadata to allow from keeping keeping the consistency of the data. And of course, as I mentioned about the spill to disk, this is a key issue, especially with the traditional compaction engines that we were able to solve. And then commit interval is another important decision. For RisingWave, the commit interval is at a second because we are ultra low latency. The default is at 1, so the data is guaranteed to be fresh for a sub-second. But the problem with such an aggressive low commit interval is that it will create a lot of small files. You have a lot of small files scattered across, which is not very conducive for Iceberg because of the fact that it's a columnar format. The Parquet files are not they're not built for that kind of scale. So in this case, we've configured the commit interval to be at 60 seconds, assuming that's sufficient for a lot of the use cases. Especially for analytical use cases, you can tolerate up to a minute of data freshness latency. But again, this means you, if you want to override that, users have a choice to lower that commit threshold from 60 seconds to a lower knob. Because the downside is you'll have a lot more small files, which means your compactor would have consumed a lot of compute resources. That's a trade-off that the user can make. And then also with this, if you want to make the writes immediately available, we provide a flash command that user can use. For example, on demand, they can instead of lowering the threshold, they can just use the flash command as an override mechanism. And then the last thing on the consistency side, to achieve the required consistencies, I mentioned about the fact that we have two copies here, right? Like the metadata copies. One is the RisingWave tables which have the internal store that have our own custom data store versus Iceberg which has the external one. So sometimes what happens, how do you make sure the consistency is guaranteed? So again, here we track since we store since the log store is the same, right? We use the same object store for the internal store also. We track the offsets and then we track for each snapshot what is the pre-commit Iceberg tables are, and then ensure that we are able to maintain consistency. And then the single source of truth for this system would still be the Postgres metastore that RisingWave runs, because that's the single copy. And that will ensure that if there is any inconsistency between the two systems, the Postgres equal metastore that's part of the Rising system will be the single system code. And I've included some RFCs in the presentation. I know if you can see at the bottom, there are a bunch of RFC design docs. If you are, this is a fairly high level talk, right? I'm just going at a surface level more to cover the breadth of all the things that we did to support this. If you're interested in knowing each feature, for example, compaction or consistency or any of those links at the bottom with the RFCs will give you a good deep dive into what the implementation looks like. It's an open source product, so everything's available for you to review. That's pretty much it from my side.